Okay, young ones, time for discussion 7.2. This is going to be on enthalpy, entropy, and specific heat. I'm going to go through this one kind of quick, so if you need to copy stuff, just pause the video. All right, so what is specific heat? Specific heat is the amount of energy that's needed to raise the temperature of 1 gram of a substance by 1 degree. So remember, in this unit, when we're talking about energy, we're talking about heat. So it's the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So we talked in discussion 7.1 about how when something gains heat, its temperature increases. Specific heat is the specific amount of energy needed to increase the temperature. Or conversely, it's the amount of energy needed to be lost to lower the temperature. So since specific heat is the amount of heat needed to change the temperature, if something has a high specific heat, that means it is going to take a lot of energy to change its temperature. So things like metals have low specific heats, so they will heat up more quickly. A nice example of this is heating up water in a pan. So you pour a little bit of water into a pan or a pot from your sink. It's not very, it's, room temperature. You put the pan on the stove and turn it on. You've only been heating the water for about 30 seconds. So even though it's been heated, the water didn't heat that much. So it's perfectly fine to dip your finger in it. But because the metal has a lower specific heat, you probably wouldn't want to touch the metal pan. Because even though the pan and the water have absorbed the same amount of heat, because the metal specific heat is lower, it will experience a greater temperature change. Or think about sand on the beach. At the beach, sand heats up faster than the water because sand has a lower specific heat. So just imagine it, you step onto the beach, yow, it's a little hot, your feet are burning. So where are you going to run to? You're going to run to the water because the water is cooler. The water and the sand have absorbed the same amount of solar energy because the sun came up for both things at the same time. But because the water's specific heat is higher, it experiences a smaller temperature change. So you might be faced with a problem like this. It says, which metal would experience the largest temperature increase when 200 kilojoules of energy are absorbed? That means each metal is absorbing the same amount of energy. So we got 4 metals: lead, tin, iron, and aluminum. Because lead has the lowest specific heat, it will experience the largest temperature change. All right, so we can do calculations using specific heat. The equation we use is Q equals M times C times delta T. So in this equation, Q is heat. And remember, heat is measured either in joules or kilojoules. Lowercase m is always mass, and mass is measured in either grams or kilograms. C is our specific heat. So the unit of specific heat is joules per gram per degree Celsius, or kilojoules per kilogram per degree Celsius. So remember, specific heat is the amount of heat per gram per degree Celsius, which is where we get that unit. Finally, delta T. This little triangle is the Greek letter delta. In science, delta always means change. Capital T always refers to temperature, so delta T is the change in temperature, and temperature is measured with just degrees Celsius. When we're calculating the change in temperature, it'll always be the final temperature minus the initial temperature. So the initial temperature is the temperature that the substance starts at, and the final temperature is the temperature it ends up at. It's really important that you always do final minus initial, and I will show you why later. All right, so remember, there are 1,000 joules in 1 kilojoule, and there are 1,000 grams in 1 kilogram. That means when we're plugging into this equation, if the mass you plug in is in grams, when you calculate Q, Q will have a unit of joules, because the unit of grams cancels with the unit of grams in the specific heat. The unit of Celsius in the temperature change cancels with the Celsius down here, leaving us with joules. But if the mass you plug in is in kilograms, then Q will be in kilojoules. Because if our mass is in kilograms, when we multiply by this specific heat, the kilograms cancel. Degrees C leaves us with kilojoules. All right, so let's look at an example. This one says a 155 gram sample of an unknown substance was heated from 25 to 40 Celsius. In the process, the substance absorbed 5,696 joules of energy. What is the specific heat? So one really important thing to do, especially when facing these word problems, is actually label the problem. Label each of the variables, because when you label them, it makes it easier to organize the information, and it makes it less likely that you're going to make a mistake when you're plugging the values into the equation. So when I read this, the first thing, what is going to tell us what's what? The units. So the first thing I see is a unit of grams. Grams is a mass, so put a little m over it. It was heated from 25 to 40. Those are temperatures. It's going from 25 to 40, making 25 the initial temperature and 40 the final temperature. In the process, the substance absorbed joules of energy. Joules is Q. What is the specific heat? Specific heat is C, which is our variable. So the equation we're going to use is Q equals mc delta T. What a lot of kids will do, since we're solving for C here, they'll plug in the values and then they'll rearrange it. But the easier way is to rearrange the equation first. All right, so here's the equation we're using. If I'm solving for C, there's C. I got to get the delta T and the M over to the other side of the equation. The M and the delta T are connected to the variable with multiplication, so we're going to divide M and delta T from both sides of the equation. When you do that, the M's cancel and the delta T's cancel. C remains, leaving us with C equals Q over M delta T. Now we'll plug in the variables. I strongly recommend when you do this, you calculate delta T first, because delta T is calculated with subtraction and the rest of the equation is multiplication. If you're going to put it in your calculator all at one time, you have to put the subtraction part in parentheses. But if you do it first, you don't have to worry about it. So let's do it. Delta T is final minus initial. Final was 40, initial was 25. 40 minus 25 equals 15. We now have our Q, our M, our delta T, and we're trying to find C so we can plug into the equation. C will be equal to Q, which is 5696, over M and over delta T multiplied together. So M is 155 times delta T, which is 15. Again, notice the parentheses. It'll be 5,696 divided by 155 divided by 15. Remember, because both those numbers are down below. When you do it, you get 2.45. The unit of specific heat is joules over grams degrees Celsius. The mass we plugged in was in grams, so it's joules. If it was kilograms, it would be 0.155 kilograms, and then the unit would be kilograms. But since we plugged in grams, it's joules. That's your answer, so put a box around it. All right, try this one all on your own. Pause the video, see if you can work it out. Read the problem, label all the variables, and then solve. Please note, we want our Q in kilojoules. So pause the video and try it out. Okay, so let's read and label as we read. This says how much heat in kilojoules. So I automatically know that Q is the variable because it's asking us how much heat is required when 1,255 grams, gram is a mass, so put an M over it, of water is heated from 0 to 100, making 0 our initial temperature and 100 our final temperature. And it says the specific heat of water is 4.18. Specific heat is C. So we're solving for Q this time, so no rearrangement required. Start by calculating delta T. Delta T is final minus initial. Final is 100, initial is 0, so delta T here is 100. Once we have delta T, we can just plug the variables in. So it'll be mass times specific heat, times change in temperature. When you do that, you get 525,000 joules. It's joules because we plugged in our mass in grams. We need kilojoules though, so we're gonna have to convert those joules into kilojoules. We're gonna plug in our conversion factor, dividing by the 1,000 joules so that joules cancels, and that'll give us 525 kilojoules, which is your answer, so put a box around it. All right, now let's talk about enthalpy. Enthalpy is denoted with a capital H. Now, when I show you the definition for enthalpy, what you'll notice is it's very similar to the definition of Q, but it's a little teeny tiny bit different. Enthalpy is the change in heat that occurs during a chemical reaction per mole of the limiting reactant. What's the difference then? Q is the total change in energy. Delta H, the change in H, is the energy change per mole. So that means our unit of delta H will either be joules per mole, energy per mole, or kilojoules per mole. So when we calculate delta H, we need the number of joules, which is Q, and we need the number of moles. So the equation for calculating it will be delta H is negative Q divided by N. The Q is the heat given off, the total amount. The N is the number of moles of the limiting reactant. I'll explain in a minute why it has to be negative Q. All right, so let's look at an example. It says 150 grams of water was heated by fully burning 2.3 moles of gasoline. If we fully burned it, that means the gasoline was limiting. The temperature of the water changed from 25.8 to 97.1. Calculate delta H in kilojoules per mole of gasoline. And of course, the specific heat of water is 4.18. So to get delta H, we need Q and N. So the first thing I got to do is calculate Q. To calculate Q, we use MC delta T. When we plug in, it's the mass of water, which is 150, times the specific heat of water, which is 4.18, times the temperature change, which will be 97.1 minus 25.8. But don't forget, read the problem. Grams is mass, moles is N, initial temperature, final temperature, and C. So now let's plug in. Mass is 150, specific heat is 4.18, temperature change is 97.1 minus 25.8. When you plug it into your calculator, you get 44,700 joules. But we need kilojoules per mole, so we should convert that joules into kilojoules by dividing by 1,000. When you divide by 1,000, 44,700 becomes 44.7 kilojoules. Next, we just have to calculate delta H. We calculated Q and we're given N, right? So we're just going to plug into the equation delta H is negative Q divided by N. Well, remember it's negative. This is positive, so when we plug in, it'll be negative 44.7. Divided by 2.3 moles gives you negative 19.4 kilojoules per mole. That's your answer, so put a box around it. Now let's look at one more example. Now this example is just what we are going to do in Lab 7-2. So do make sure that you take really good notes here and use these notes to do the lab when we do it in class. All right. So it says 2.5 grams of ammonium nitrate was dissolved in 100 grams of water. The temperature of the water went from 25.1 to 1.1 degrees Celsius. Ooh, it got colder. Calculate delta H for this process in kilojoules per mole of ammonium nitrate. All right, so there's a couple things. First of all, kids have trouble figuring out which mass we plug into Q equals MC delta T. But remember, when we're plugging into an equation, the variables in the equation have to always be for the same substance. So the water is changing temperature. We're given the specific heat of water. That means the mass we plug in will be the mass of water. Another thing that will tell you that is it tells you kilojoules per mole of ammonium nitrate. All right, so first thing we're going to do again is calculate Q. Let's go ahead and label the variables in the problem though. We're going to be using Q equals mc delta T. 2.5 grams is a mass. 100 grams is also a mass. The temperature of the water goes from 25.1 to 1.1, making 25.1 the initial temperature and 1.1 the final temperature. We're given the specific heat, which is C. So when we plug in, it'll be the mass of water times the specific heat of water times the temperature change. 1.1 minus 25.1 gives us negative 10,000. It's joules because we plugged in grams, but we need kilojoules. So I got to convert that amount to kilojoules. So negative 10,000 joules divided by 1,000 will equal negative 10 kilojoules. Now that we have Q, we need N. Remember, N is always moles, but we're given a mass of this salt. So to convert from mass to moles, we need to use the molar mass conversion factor. We're starting with 2.5 grams. I need one step in my fence to do it. The molar mass of ammonium nitrate goes down below. 80.06 is the mass of 2 atoms of nitrogen, 4 atoms of hydrogen, and 3 atoms of oxygen, or at least 1 mole of each of those. So I calculate 0.031 moles. Now I have Q, I have N, so we can calculate delta H, which uses delta H as negative Q divided by N. This is the Q. This is the N. So all we have to do now is plug the values into the equation. So delta H will equal, this is negative 10, and it's negative Q, so it's got to be positive 10 divided by the number of moles equals, in this case, 323 kilojoules per mole. That's your answer, so put a box around it. All right, moving right along. Last thing we're going to talk about, second to last thing, potential energy profiles. A potential energy profile is a graph that shows how energy, changes during a chemical reaction. There are 5 sections or segments of this graph, A, B, C, D, and E. If we look at the y-axis, it's potential energy, and the x-axis is reaction progress, or essentially time. So A is a horizontal line at the beginning of the process. So A is the energy of our reactants. Recall back to Unit 5, activation energy. You have to put energy into reactants in order to get them to go. So if A is the energy of my reactants, as we add energy, the energy goes up, it goes up, it goes up, it goes up, it goes up. Once it gets to a certain point, once you've added enough energy, boom, the reaction can happen. So this region of the graph labeled B is the activation energy. And the symbol for activation energy is a capital E with a subscripted A. C, which is right at the top of the hump, is called the activated complex. It's called the activated complex because it represents all the reactants that have enough energy to form new bonds via successful collisions. D over here is the energy of the products, and E is another region of the graph between the energy of the reactants and the energy of the products. It's the total change in energy. So that area of the graph represents delta H. All right, you can also tell from an enthalpy or for potential energy profile. By the way, I left this slide here because they're also called enthalpy level diagrams. You may see both. So for an exothermic reaction, exo means heat was lost. So in an exothermic potential energy profile, the energy of reactants will be greater than the energy of the products. The region of the graph between the energy of reactants and the top of the hump is the activation energy, and the region of the graph between energy of reactants and products is delta H. For an endothermic reaction, that means energy must go in, So for endothermic, our products will have more energy than our reactants. The activation energy still goes from the reactant line to the top of the hump, and delta H is still the region between the energy of products and reactants. Notice for the endothermic reaction, the activation energy is much greater, which is why we have to put energy in. For an exothermic reaction, we got to put a little bit of energy in, but we get more energy out. So another way to look at this, in an exothermic reaction, there is an excess of energy because we put in this much and got that much out. For an endothermic reaction, you need additional energy because the activation energy is greater than the amount of energy you get back. So for an exothermic reaction, delta H will always have a negative value because it represents a loss of heat. And for an endothermic reaction, delta H will always be positive because it represents an increase in energy or the addition of energy. All right, so take a minute, use this actual potential energy profile to calculate the activation energy and delta H for this process. All right, so first of all, I know this is for an endothermic reaction because the products have more energy than the reactants. The activation energy goes from the energy of reactants to the top of the hump. The energy of reactants is at 100. The top of the hump is at 400. So this region represents 300 total joules. 400 minus 100. Delta H is represented by the letter C here. It goes from energy of products to energy of reactants. The products have 300 joules of energy, and the reactants have 100, and 300 minus 100 equals 200 joules. Uh-oh, the kids are coming. They're going to have to wait because I got to finish. All right, last thing I got to talk about really quickly is called entropy. Entropy is a capital S, and it represents the disorder or randomness of a particular system. The more disorder the system has, the greater the entropy. So there's three main things we can do to affect entropy. One, we could change the number of particles. More particles mean more disorder, just like more cars on the highway mean a less ordered highway. We could also change the state of matter. Solids have particles that are very well ordered. They don't move around in relation to one another. But gases, because the particles move crazy, have the highest entropy. And you could also increase temperature because higher temperature means the particles are moving faster, and the faster they're moving, the more random things are. All right, so which has more entropy, a sandcastle or a pile of sand? To answer this question, you just got to think about which structure is more ordered or less random. Obviously, the pile of sand is more random. The sandcastle is an organized order of those sand particles, so the pile of sand has more entropy. Liquid water versus steam, well, gases always have more entropy, so steam will have more entropy. And finally, cool water versus warm water, well, as you increase temperature, entropy also increases, so the warmer sample. That is it for topic 7.2 and unit 7 as a whole. Thank you so much for watching this video, and I'll see you in class.